Welcome back, boys and girls. We're going to have another lesson in pre-calculus, and today it is on discontinuity and domain, where we're going to focus in with an algebraic approach instead of just looking at the graphs. But before we get into the lesson, I got to tell you, today I'm going to be in the lesson. I think I'm the first Algebro to actually attempt this. We're going to see how it goes. Hopefully this will not be too distracting. I apologize for the audio because in order for me to do this, I have to take off my headset. I don't think if I put this on, I think I'd look kind of like a doofus in the lesson, so I'm going to keep that off. And when we're done here, I'll have him make a comment or something down below, see if this is too distracting. Okay, let's jump into the beginning of our lesson here. Let's remember what we did in our last unit, and that was the types of discontinuities. The first one was a removable discontinuity, which is basically a hole. So something like that one right there, that would be just a hole. If we had a non-removable, it would either be a jump discontinuity like this, that's non-removable, or a vertical asymptote. Now in this lesson, we're just going to focus on the vertical asymptotes. We're not going to worry about jump discontinuities. So that's why I put here vertical asymptote. And then we could also have a situation where there are no discontinuities, meaning the graph is just continuous all along the way here. There's no breaks or anything like that. So that would be something called continuous on its domain. We'll talk about that in a minute. Then domain. So we have our discontinuities. There's the three types. Either it's a hole, vertical, or there are none. The domain is referring to all the possible x values of a function. Or another way of thinking of this is, where does the thing exist? I'm looking at where does the function exist. Wherever it is, that's the domain, all the x values. So let's do our first examples. We're going to find discontinuities for each of these functions and classify them. So how do we find it? This right here down on this, put this on like the side of your notes or something so you can have it written down in your margin, because it is very important. The way you find a discontinuity is you set the entire denominator equal to 0 and you solve. Okay? That's how you find a discontinuity, where the graph has a break in it. How you classify it is you look at the factor. If the factor canceled, then there's a hole there. If it doesn't if it doesn't cancel, if it stays there, then there's a vertical asymptote, usually. Okay, I'll come back to that. So write this down, pause right now, write that down if you don't have it, because I'm going to start doing example number 1. And here's how it works. The way we find it is we set the denominator equal to 0, because denominators cannot equal 0. And then when we solve this thing, we get x is equal to -1. That's where the discontinuity is. It's at x equals -1 of this graph. Now, what type of discontinuity is it? A vertical asymptote. I'm going to abbreviate this. VA. Vertical asymptote at x equals -1. And that there is my answer. Okay. So how do I know it was a vertical asymptote? Because this factor right here, this x plus 1, did not cancel with anything in the top. Therefore, since it stayed, it is a vertical asymptote. Now, there are things that would have a jump, but you'd have to have like a piecewise function, or you'd have to have maybe an absolute value inside the numerator. I'm not going to give you those in this lesson at all if you're just finding discontinuities. Okay, you don't have to be able to know how to do that part. At least I hope I didn't. If I did, I'm sorry. I don't think I put those in the practice. Next, number 2. Okay, so we're going to take the denominator, set it equal to 0. That's how we find the discontinuities. See where their breaks in the graph are. So we take x plus 3, solve it. You get x equals -3. That's the first one, first discontinuity. And then we take this thing. How do we get rid of the square root? You square both sides. So remember, this is a zero product property where you take the first factor and the second factor, you set them both equal to 0 and solve it. So we'll take this one and we square both sides. So you square both sides and you get x minus 2 equals 0. Square root's gone. Solve it, you get x equals 2. Okay, so then this one, this represents a hole. So I'm going to put that this one is a hole. Now, why do I say that it's a hole? Because, let me box this, because right here, the factor of x plus 3 is canceling with the numerator that is an x plus 3. So it is a removable, since it removes, it's a removable discontinuity, which therefore that means it's a hole. So instead of writing out the whole phrase removable discontinuity, we're just going to say that it's a hole for for brevity's sake. And then this one is a vertical asymptote at x equals 2. So we'll just box those together there to make sure that you can tell this one's a vertical asymptote, that one is a hole. Or you could write it out like this. Okay, number 3. Let's try this one. So denominator, set it equal to 0. That's how we find discontinuities. And solve it. Well, how do you solve this thing? There's no x in the denominator here. You can't solve it. 4 does not equal 0. Not possible to solve it. Therefore, the answer to this thing is this cool phrase. It is continuous on its domain. This phrase means there are no discontinuities. There just are none. But this is the phrase we use. It's continuous on its domain. So wherever the graph exists, there it is continuous. No discontinuities. Next slide here, I don't have all the things written down there on the bottom, so make sure you got them written down on the side of your notes if you don't have it yet. And number 4, let's do this one. We're going to say that it equals 0, and to solve this thing, so we got to start factoring all this stuff. So let's take down an x.
We have x times x squared plus 5x plus 6. I think I'm going to speed this up if I haven't already, because I'm guessing you probably know how to factor these things. This becomes x times x plus 2 and x plus 3 equals 0. Use the 0 product property, we're going to get x equals 0. We're going to have x plus 2 equals 0, so that ends up being x equals negative 2. And we have x equals negative 3 when you solve for all three factors. Okay.
Now we have to recognize, did anything cancel? So did this factor, or this factor that are all in the denominator, did it cancel with anything in the numerator? No, it did not. Nothing cancels, and that means that all of these are going to be vertical asymptotes. So we have a vertical asymptote at x equals 0, vertical asymptote at x equals negative 2, and a vertical asymptote at x equals negative 3. And the nice thing for your teachers is when you show your work on these things, if you could box them together like that, and therefore we can quickly and easily see that the vertical asymptote is going with each individual discontinuity, that you know what it is. It represents vertical asymptote on the graph of this. Okay, you're going to pause now. Try number 5 and number 6 all on your own. See if you get your answers, then push play again, and you'll see if you get the same answer that I get. All right, pause now. And there's your answers to numbers 5 and 6. You can see here x equals negative 1/2 is a whole, x equals 7 is a vertical asymptote, and the reason is when you factor this denominator here, you get a 2x plus 1, and that cancels with the 2x plus 1 in the numerator. So there we go, whole and vertical asymptote. This one was continuous on its domain because when you take the denominator, set it equal to 0, it's impossible to solve it, so you're done. Nothing to do. You say it's continuous everywhere because it's not possible to have a 0 in the denominator in this case. Okay, so we're done with the first part, which was discontinuities. Now we're going to move on to domain. Before I do that, I got to show you something. One of the reasons I want to try this out is to try different things that let's see if this works. Okay, I'm gonna climb up here, the very top of the screen, and I'm holding there. And if I look down and then let go, and oh, okay. See, I can't do something like that if I'm just behind a microphone. Okay, going on here. Domain. The domain is where the function exists. The first part, this first line, the whole way across here, we're going to focus on just letting the denominator that it can't be 0. Okay, it's just like finding a discontinuity, but in this case, what we're really saying is we're making sure that we understand that this thing cannot be a 0. That's the domain. I know it's just like discontinuity, but you'll see a little bit of a difference here. So when we solve this, we're going to say that x cannot equal negative 1. So the domain of this thing is everything. If I was doing interval notation, okay, don't write this down. Don't write this down. If I was doing interval notation, I would do this. Negative infinity, comma, to negative 1. Oops. Negative 1, and then union with a negative 1 to infinity. Okay, here's the reason why I don't really like to use this. Because interval notation for this is kind of long. I know that might make sense, but really you can just say this. This is so much easier. We're going to use inequality notation by just saying, look, it's all real numbers except that it can't be a negative 1. So it's everything except that point right there, that x value. Okay, that's a lot better way of giving an answer for what the domain is. Okay, so we're not going to worry about interval notation. Oops, let's get rid of that and that. There we go. Okay, so that's what we're looking for. Let's do number 8. Actually, I got a little pause dude here. So factor number 8 and then list an answer for what you come up with. Okay, so pause the video. All right, this is how I would do it. Factor around the denominator. This should have been very similar to one we already did. And then you get that t can't be a 0, a -2, or a -3. Okay, so therefore the domain of this function is all real numbers, but the x's can't be a 0, -2, -3. Okay, there's the domain. We don't have to worry about whether or not it's removable or non-removable, like if it's a whole or vertical asymptote. That doesn't matter for finding the domain. We're just saying, where does this graph exist? All right, number 9. So in this situation, for number 9, we have that 2 cannot equal 0. Well, yeah, that is always going to be happening. It doesn't matter what you plug into x. 2 will never equal 0. Therefore, in this case, we just say all real numbers. The domain of this thing, because that's what we're finding. Where's the domain? The domain is all real numbers. Okay, number 10. Now on this row down here, we've got radicals. So if you look over here, when you read this, you don't read this as even radicals can't be negative. You're supposed to read it as even radicals, like as opposed to not the ones that are odd. So we're saying ones that are not odd. Even radicals like the square root, the fourth root, the sixth root, things like that. If you have an even radical, then they can't be negative. So you take what's ever under the radical. In this case, it's 7x plus 3. Take 7x plus 3. You just say that it can't be negative by saying greater than or equal to 0. It's okay if it equals to 0. It just can't be less than 0. And then you solve it. So when you solve this thing, you're going to end up with x is greater than or equal to -3/7. Please show your work if you're getting a little confused on that. I know I just skipped steps and went straight to the answer, but yeah, you know, you should be able to solve those little two-step equations. The domain of this graph, of this function, is that all of the x values have to be greater than or equal to -3/7. They can't be smaller than that, or else it would make this a negative. So there's the domain. And you could graph it yourself and see that's what it's doing. Number 11. Now 11 and 12, this gets a little trickier because we have both fractions and radicals going on. So up here we had where you were dealing with fractions and you had to focus in on the denominator, so fractions, and then down here we have radicals. Here we have both. So the way this works is you got to take both situations. So how about we say, let's take 5 minus x, because that's what's under the radical, and just say that it is greater than or equal to 0. So when you solve that, you get -x greater than or equal to -5, and then divide both sides by -1. You get x is less than or equal, make sure you flip that thing, it's less than or equal to 5. So the x's have to be less than or equal to 5. But then we also have a situation where we say this thing can't actually equal a 0. So we have to go back up here where we were looking at denominators, and when you solve that thing, you are going to square both sides. You get 5 minus x, that can't be equal to 0. And then you solve this thing, you're going to get x cannot equal -5, it can't equal 5. So you have these two statements. You have to do the most restrictive part of this. So you're saying x has to be less than or equal to 5, but it also can't equal 5. So the answer would be x is less than 5. Okay, so then we box that. So x being less than 5 makes it fit the criteria that we're saying it has to be less than 5, but it also can't equal 5. So boom, there we go. Okay, whatever is most restrictive, that's the answer to these problems. Number 12. Let's do the same type of thing. Okay, so we say that the bottom cannot equal 0, and whatever's under the radical has to be greater than or equal to 0. Let's do the radical first. So 2x minus 6 greater than or equal to 0. Solve that thing, and we're going to end up with x is greater than or equal to, so we added 6 divided by 2, 3. Okay, so x has to be greater than or equal to 3. Next, you solve this thing, and you're going to get x cannot equal negative 5, and it also cannot equal 5. So you subtract the 5, add the 5. So it's these two things here. So let's take all three of those. It's got to be greater than 3. It can't be negative 5, and it can't be a 5. So what in the world's going on here? This negative 5 here, we completely ignore this part right here, that it can't be negative 5. It doesn't matter because we already know that x has to be greater than 3. So our answer is all of the x values that are greater than or equal to 3, but also x cannot equal 5. So we put this little thing in there. It's all the numbers that are greater than or equal to 3 except for 5. And there it is. Okay, almost done. Just 2 more problems. If you need to rewind those, I know that's pretty confusing, then go back and look at it. Now we're going to put them all together. Last 2, we're going to find the discontinuities, and we're going to find the domain. Put on the side of your notes here that when you do both together at the same time, it's better to find the domain first. I know we practiced discontinuities and then we practiced domain. Find the domain first when you do this. Okay, side of your notes, put that down, and I'll show you why here in just a second. When we find the domain first, so we're going to say defining the domain is that the denominator cannot be a 0. So we say t cannot equal 0, and then we use the zero product property, and then we say the square root of t minus 5 cannot equal 0. Solve this thing, you're going to end up with t cannot equal 5. Okay, so we've got t can't be a 0, t cannot be a 5, and what else? Whatever's under the radical, which is t minus 5, that has to be greater than or equal to 0. When you solve this, you get t is greater than or equal to 5. So the restriction on the domain is what? What's the most restricted thing? It can't be a 0, it can't be a 5, and it has to be greater than or equal to 5. Okay, well, greater than 5 means we don't have to even worry about this thing right here. We don't even worry about it because it's got to be bigger than 5 for the domain. So that thing means nothing. And it also can't equal 5, so the domain answer is t is greater than 5. Remember, we're looking for the most restricted thing of these 3 things for the domain. Now let's find, what are we looking for? Oh, the discontinuities. Find the domain first, now the discontinuities. So the discontinuity would be, well, have a t equals 0 here, so you take the denominator, you set it equal to 0, but we don't have to worry about this one. Let's just do it down here. So we take the first part of the denominator, set it equal to 0, solve it. Okay, that's solved. Take the second part of the denominator, t minus 5, this other factor here, set it equal to 0, solve that. You're going to get t equals 5. Square both sides, add 5 to both sides. So these 2 things are where we have either holes or vertical asymptotes. But, okay, you got to think about this, vertical asymptotes, holes, that would only make sense if it's within the domain. This right there, that's not within the domain. And this right there, that is not within the domain because it's got to be only greater than 5. So the answer then, if we slide these things down, get them out of the way, the answer to where is a discontinuity, there are none. There are no discontinuities because you have to focus on the domain and the graph only exists greater than 5. So therefore you say it is continuous, we'll abbreviate that, on its domain. Continuous on its domain. Okay, we find the domain first, and then using that, you can help identify whether or not you have holes or vertical asymptotes. It would only count if it was within the domain. All right, number 14. This would be a good one to pause. I don't have a little guy here who's thinking, but let's do it. Pause the video now. This is the very last problem, and then you can see if you get the answer correct. Okay, pause. All right, there's your answers to number 14. I've got the domain. Remember, you had to find the domain first, so I said that the denominator cannot equal 0. So then I solved that thing. I got that a cannot equal 4. And then I set whatever's under the radical has to be greater than or equal to 0. Solve that, and there you go. So the domain was those 2 things combined. So it's a is greater than 0, but a cannot equal 4. There's your domain. Then I found the discontinuities by just taking the denominator. So remember, discontinuities is only the whole denominator. You just take the whole thing, set it equal to 0, solve it. And that gave me 4. And since the thing didn't cancel with anything in the numerator, it's a vertical asymptote. There you go. You finished. So the lesson is over. What I'm going to do, if you're at all confused about this lesson, here's a very brief summary. Okay? For those of you who are done and you got it, then if you want to comment down below, you can. You're not going to hurt my feelings, I promise. You like having one of the Algebros in the lesson, like a small little excerpt, or now you don't want to see us at all. We're too distracting. Okay, so lesson summary. Boom. First thing, we're finding discontinuities. How do we find discontinuities? You take the denominator, you set it equal to 0, and you solve. That's how you find a discontinuity. If the factor canceled, it's a hole. It's one of those little gaps in the graph. If it didn't cancel, if it stayed there, then it's a vertical asymptote. Denominator equals 0, solve. There's finding discontinuities. Okay? Now, finding domain. If you find the domain, which if you have to do both of them together on the same problem, it's easier to find the domain first. Find the domain first, and that helps you with discontinuities. Finding the domain is that denominator can't be a 0. Okay, so it's kind of like the discontinuities, but you say it can't be a 0, and you also have to have positive or 0. You can't have negative things under a radical. Well, an even radical. Okay, there you go. Lesson summary, we're done. Rock that mastery check, and I will see you back in lesson 2 for unit 3.